Okay, that was quick. You're already listening this. So what we are doing in this lecture, it's a follow-up from the 7.4.1, and we will now develop the tight binding model for a one-dimensional chain of atoms. And essentially, we will do the math, and we will see that if you have a kind of non-zero hopping term, we actually get a dispersion relation out of this simple model. So we see that we get similar ingredients out from the tight binding model that we got out from the free electron models and the nearly free electron models. So essentially the hopping term here that we will be showing to you soon, it seems to be quite related or analogous quantity that we had when we were describing in the free electron models a non-zero periodic function. We were using that kind of non-zero periodic function to describe things, and we saw that the periodic nature of things and some kind of coupling between the electrons gave rise to the dispersion relation. So we are seeing exactly that here also, that when we start having a possibility that the electrons are being coupled or they can move around, then this possibility gives rise to the dispersion relation of the system. So that's what we will do here in this lecture, and I will now continue with what we were able to establish in the previous lecture. So we were solving the eigenvalue problem. So the Schrödinger equation was being cast into an eigenvalue problem, and we were considering only a single orbital associated with each of those atoms. So the bras and kets where we had n's and m's, each of those meant that this is the single orbital associated with the nth or mth atom, and we had a one-dimensional chain where we had in total capital N number of atoms. And now the question mark that we were not able to solve up to this point was that or decide up to this point was that how did these potential operators look like? So we had that equation in the previous lecture, and we had this kind of summation left over where we were summing over j's, so different kind of potential operators, and we ensured that we did not sum over m anymore, so that was taken out earlier from the summation. And then we have this kind of bra n multiplying the operator j, potential operator j, and when we had the get of m. And now we assume, and this is often made, that we just simplify this operator and summation of that. So we just assume that for the case of n equals m, the operator is simply v naught. And then for the case when n is m plus 1 or minus 1, that then we have the operator equal to minus t. So it's a coefficient minus t, and this is known as a hopping term, and that kind of physically would give us a possibility that the electron state would move around to adjacent atom. And otherwise we assume that the potential operators are zero, so nothing much happens. So t parameter is known as a hopping term because physically it means that this electron state can hop around. So it can move from the nth atom to the adjacent atom. So n plus 1 or n minus 1. And this, now we can define the energy to be and the kind of total energy associated to be epsilon naught. And then this is the kind of atomic energy associated with an individual atom's orbital. So please remember what we discussed in the previous lecture, plus this V naught term arising from the fact that we do have some kind of potential operator in addition operating on these states. So we know that what this looks like is that we're kind of like having an energy that looks almost like the eigenenergy associated with a single atom's orbital state, but it's being slightly modified by this term. So it's almost, but not exactly that. And then in addition, we have that hopping term, and let's now look how the matrix elements will look like subsequently. So please remember, I did not explicitly show the math in the previous lecture, but we had exactly this matrix element used the earlier equation. So we had this bra of n multiplying the Hamiltonian operator h hat, and then we had the ket of m, and we used this simplification notation. So now what we're doing is that we're exactly solving this. And we can now found that. So we have the total energy epsilon naught, or the newly defined energy, and we are multiplying that with the Dirac delta function of nm, because this only is the energy associated with the case that the n equals m. And then we have the term arising from the hopping term, so that when this will be non-zero when the n is or m is equal to n plus 1, or m is equal to n minus 1. So this is essentially arising from the fact that we have this kind of assumption that this is how our potential operator looks like. So this is basically arising, giving us this. And this is already familiar looking math that we were using in terms of understanding the dispersion relation of phonons in chapter 4. So we it seems solvable already. And how do we solve this is that we assume that we have some kind of trial solution, and for simplicity we assume that we have this kind of formula. So we have a kind of like plane wave looking component exponent ikNa divided by n square, or square root of n. So we have normalized things, and we can plug this into the earlier equation. So then we have the matrix component of the Hamiltonian equals epsilon naught times the Dirac delta function of nm minus the hopping term t, multiplying those Dirac delta functions. And we can plug this into our earlier equation. So please remember the Schrödinger equation was being cast into this form. And here we have the Hamiltonian matrix components that are looking like this. And then we have these different phi m's and phi n's here that we assume that are of this form. That they are kind of something that they comply with the periodicity of the problem. So that here we have the lattice constant, and we have a one-dimensional chain of atoms. And then we have this eigenenergy associated with this state. So we mindlessly plug in into this equation, into the summation what we have. And what we have out is that we have the epsilon naught multiplying the exponent minus ikNa divided by the square root of capital N minus the hopping term t, multiplying things inside the parentheses. So now we place in, instead of n, we have n plus 1 in the exponent divided by n square root, plus then we put in the n minus 1 instead of n into the exponent. So this is what we get out. And then on the right hand side we have the energy, and we multiply that with the phi n, and phi n now is with the trial solution of a form of exponent minus ikNa divided by the square root of n. And looking at this, in all of these terms, we have this square root of n that we are using in the denominator, so we can vanish that. And in each of these exponents, we have the minus ikn term here. So we have this in all of these terms essentially. So we can also divide that out, so that what we get out, what follows is that then we have the epsilon naught multiplying, minus t multiplying the exponent minus ika plus exponent plus ika. And then on the right hand side, we have the energy. So now this is actually quite nicely looking equation already, so that the things don't look that bad. And we can now simplify things further. Some folks prefer sines and cosines over exponents, so let's do that. So we can recall that the cosine function, of course, cosine x is exponent minus ik plus exponent minus ik. Cosine x is exponent ix plus exponent minus ix divided by 2. So the familiar dispersion relation follows. So that the energy that we had on the right hand side of the previous equation now is equal to epsilon naught minus 2 times t times cosine of ka. So please note, cosine of x is essentially the real part of exponent minus ix. So it's of this form, like I mentioned already. And because I have this here, that turns to be the multiplication here, and then we have the cosine Ka here. And this is the kind of dispersion relation that we have seen already to take place in the simplest of cases. And this is what we were seeking. And it's quite nice to see that when we just have a non-zero Hoping term, so we just ensured that the electron state can move around to the nearby atomic sites, that this is what gives rise to the dispersion of the system. So it somehow seems to be related to this fact that we had a periodic potential, and somehow that was being coupling the system and giving rise to a dispersion relation. But here, the coupling in a way is more like an electron being able to hop around. So these processes are somehow connected, or they seem to be the other sides of the same coin. That's at least how I'm thinking about this. So dispersion near the bottom of the band. Let's still look how that looks like, and then let's call it a day. So nearby the value K is approximately 0. Like we can take a Taylor's expansion of the cosine term, and then what we get out, Taylor's expansion of cosine is 1 minus cosine of x, and we take the Taylor's expansion, it's 1 minus x squared over factorial of 2. So that's what we are using here, and we forget the other possibilities. So essentially, physically, we say that near the bottom of the band, the cosine looks like a parabole, and that's it. And then what we have the energy term epsilon naught minus 2t, and then we have the left over of the cosine when we are taking Taylor's expansion. Then we are left out with this x squared per 2 case. So that's why this vanishes, and this is the kind of x here if we take the Taylor's expansion of cosine of x. So this is following from that. Just a simple Taylor's expansion and forgetting the other terms plus the first two. And please note, we are interested in the effective masses in many times when we are looking at bands. The effective mass m star, or the inverse of that, was defined to be 1 over h bar squared, multiplying the curvature of the energy. So essentially the second partial derivative of the energy with respect to k. So now we can estimate that how does this effective mass, or the inverse of the effective mass, actually look like. And we can simply calculate this second derivative with respect to k. That's not that hard. And what we have out is that we have 1 over h bar squared times 2 times t times a squared, where a is the dielectric constant in our 1D lattice. So this gives us that the effective mass looks like this. So it's h bar squared divided by 2 times t, the Hoping term, times a squared, where a is the dielectric constant. And essentially this tells us that the Hoping term t affects the effective masses, or the other way around, effective masses affect the Hoping term. I guess it's a matter of taste which way we say what this equation implies. Depends, of course, on the context. But this is nice. We see that in principle, like if you would put in, for example, a larger value of Hoping term, that would seem to imply that then we would actually have a smaller effective mass. Or the other way around, if we know that the effective mass is, for example, large, then we could already imply that then the Hoping term should also have something similar in that respect. Or that that kind of like Hoping term would be remaining here, but if we would move to a different material, and we would know that dielectric, lattice constant A changes, so then we know that subsequently things should change in terms of the effective masses. And for example, if you could physically argue that the Hoping term should be the same in different atoms, we would know, in different solids, we would know that the effective mass would be changing accordingly. So this is we are now at the end of this lecture. We did not have time to cover like many more complicated scenarios for applying tight binding model, but I think as a homework, I will give you an exercise where you would be able to extend this. one possibility would be that you would, for example, extend this to a case of not a monatomic solid, but rather a diatomic solid. And we would see that we would actually have a kind of branch formation in the dispersion relation. Or another nice thing would be that we would consider, for example, what happens when we add the number of orbitals. So for example, right now we only considered that we had a single orbital. Let's, for example, say that they like a single s orbital. So we were really restricting our case to only a specific groups of elements. But if we would, for example, add another orbital there, so we would, for example, have a possibility that the electron would be in an s orbital or in a p orbital, we would be able to already understand, for example, the group 2 behavior, that how come those elements, they don't look like dielectrics, but rather they are all shiny. So beryllium and like strontium, magnesium, calcium, what are in there. So if you look into the Wikipedia, we see that they're actually quite shiny looking, so they seem to be metals. And in fact, they are semi-metals. And using a simple extension of the tight binding model, we could already understand what happens there. But let's see like what kind of exercises you will be given this year. But something interesting on the way that hopefully extends this mathematical treatment that we have outlined here. So I thank you for your time, for your great patience, and please join me soon in the final lecture that we have, where we are then considering impurities placed inside dielectric matrices. So I thank you for your patience, and please stay tuned. Bye.